Hi, in this video we are going to study about the basic functions of assembler, and we will also see how to simulate an assembler for an SIC architecture. First of all, what is assembler? The assembler, it is a program which takes assembly language as the input, and it converts the assembly language program into an object code or a relocatable machine code. So this assembly language program is produced by the compiler. So what are the fundamental functions of assembler? First of all, it will convert the mnemonic operation codes to their machine language equivalents. So, for example, the assembly language program may contain some of the machine language mnemonic operation codes, like here it is mentioned as STL. So, this may be converted into its equivalent machine language um, equivalence. And then we have the symbolic operands. So in the assembly language program, there will be the operands will be present as symbolic operands. So an example is return address. So this has to be converted into its equivalent machine address. And then we have to build the machine instructions in the proper format, and the data constants that are present in the source program has to be converted properly into its internal machine representations. For example, end of file is a data constant used in the program, so that has to be translated into the machine equivalent. And finally, the object program has to be written based on the object program format. And the assembler is a machine dependent thing. So based on the architecture or the machine for which the assembler is designed, the translation will happen accordingly. For example, the simple instructional computer SIC format, we have all the instructions will be of 24-bit format. All the instructions will be 24-bit format. The first 8 bits, it represents the opcode, and the next 1 bit, it represents the whether it is representing a direct addressing mode or indexed addressing mode. So direct addressing mode is in the instruction itself, the operand will be given. Whereas in indexed addressing mode, the content of the register plus a constant will be added to find out the location. And the last 15 bits, it represents the address. So this is the instruction format for SIC architecture. And we also have, along with the assembly language program having the mnemonic instructions, we also have certain assembler directives. We can call it as pseudo instructions. So these assembler directives, they are not translated into machine instructions, and they provide information directly to the assembler. So there are some basic assembler directives available. They are start, end. So start, it represents the beginning of the assembly language program, and end represents the ending of the program. And byte and word. So byte, it generates one byte, and word, it generates one word constant, and one word integer constant. So this RESB and RESW, it represents reserve byte and reserve word. So based on the value present in the operand, it reserve that many bytes, or it may reserve that many words according to the assembler directive given. So here is a sample assembly language program given here. So we can see here the first column represents the labels, and the second column, it represents the opcode. So these are the mnemonic instructions that are present in this assembly language program. And then we have the symbolic operands. So not all the operands are given directly as addresses, but it is given symbolically. And one more thing we want to mention here is, as we have discussed, this ninth bit in the instruction is given as either direct addressing mode or indexed addressing mode. So how we can find out whether it is a direct addressing mode or indexed addressing mode? If these symbolic operands are given directly as an address or using some of the labels, then we can assume that that is a direct addressing mode. So all these are all direct addressing modes. But whereas if the symbolic operand contains a format like something like this, a label, comma, another register. So this represents that it is an indexed addressing mode. So when we come across this, we have to represent this value of x as 1. If it is direct addressing mode, then the x value will be 0. If it is indexed addressing mode, the value x value will be 1. So here one more point we have to study is the forward reference. Forward reference is nothing but a reference to a label that is defined later in the program. For example, if you see here in the symbolic operands, a label is represented here as 0. But this 0 is only defined very later in the program. So this kind of thing we call it as the forward reference. So how we can solve this? So first we need to scan the entire source program for the label definitions wherever this particular labels comes, and we have to do the address assignment, and then we can do the actual instruction translation. So as we are trying to simulate this assembler um, using a program, we are going to see the algorithm how we can convert or how we can implement this assembler, or how we can simulate this assembler for the SIC architecture. So based on this algorithm, we can implement this. Now, first we need to open and read the input file. So, the input file consists of the assembly language program. And so, if the input line has the opcode, opcode start, okay, so we can see here in the opcode, if we have the opcode as start, then what we have to do is we have to check what is present after this opcode. If there is an operand given after this opcode start, then this operand has to be initialized to the location counter. So first we need to um, give the addresses for each of these labels. So to resolve the forward reference problem, as we have seen, first we have to give the addresses for all the labels. So the first address of this program is 4000. So the starting address of the program is 4000. If suppose this address is not given, then it can be taken as 0. The location counter can be set to 0. So otherwise, this operand can be set to 4000. So this input line can be written to a intermediate file. Now this has to be continued until the opcode is end. So until we are getting the opcode as end, we need to read the entire program, and based on the we are going to assign the addresses for all the labels, and we are going to check what is present in the opcodes also. And here we will be having we are going to use two data structures, symbol table and another one is optab. So symbol table, every time when we read this symbols or symbolic operands, we need to check the symbol table. If the symbol table contains this symbol already, then we can leave it. Otherwise, this symbol has to be entered into the symbol table. And optab, what it contains is that optab contains this particular opcode as well as its equivalent machine instruction. So as we are using the SIC machine architecture, the SIC machine architecture has some of the machine equivalents for all these opcodes. So those opcodes will be available in the optab. Now, in the optab, when we find out any opcode, then we have to increment the location counter by 3. So it is because the each word is having 3 bytes. Okay, each word here in this SIC architecture, it is going to occupy 3 bytes. And for each of the opcode, we are going to assign 3 bytes. And with that, we are going to start writing the location counter, the opcode, and the operand fields of the corresponding statement to the output file. Suppose if the opcode is word, if the opcode is given as word, then we have to increment the location counter by 3 bytes. Or if the opcode is given as byte, then we can increment it by only 1 byte. And if the opcode is reserved word, then the location counter has to be incremented by in the what is the operand value given into 3. So that many bytes we are going to reserve. Or if it is going to be reserved byte, then we have to increment the location counter by the integer equivalent to the operand value. And if we see in this example, some of that is already available. It is available here: reserve word, word. So we have seen what to do for all these things. And if there is no symbol or label, if there is no symbol or label in the operand field, then it has to be, the address has to be assigned as 0. For example, here in this case, there is no operand given. So for this, we can assign the address as 0. So as we assign the addresses like this, then we have to find out after finding out all these addresses, then we can write the object code. And to find the length of the program, we have to subtract the starting address of the program from the location counter. So that is the last location counter that we found, that has to be subtracted by this from this 4000, and that will give us the length of the program. And finally, we can close all the files. So we'll see that example how the location counter is filled up and how the object codes are found. And then we will see how to write the object program in the given format. So as we have seen here, the start represents the starting address of the program, and the operand, symbolic operand, here it shows that it is 4000. So 4000 is the starting address, and this is the first instruction. And so each opcode, it will take 3 bytes. So the next instruction, it will be in the location 4003, and this the next instruction will be in 4006 and 4009. And we are writing these addresses in the hexadecimal format. So after 9 we'll be having A, B, and then C. So the next address will be 400C. and then we have D, E, and F. So 400 F, and then we have 40. Now it becomes 1, 10, 11, and 12. Then we have 4015. Now we have to we also need to see what is the opcode given here. So for all these, some opcode is given, so we are just writing the addresses. Now coming to this point, in this address the opcode given is, it is not a actually an instruction, but it is an assembler directive saying the assembler to reserve word of 2000 bytes. So it means that we have to, it is reserve word means the given value, integer value in the operand into 3. So that will give us 6000 bytes. Okay, so word means one word is equal to 3 bytes. So here it is given in the operand as 2000. So into 3 bytes we'll be getting 6000 bytes. So this 6000 bytes is in decimal. So this decimal can be converted into hexadecimal. So when it is converted into hexadecimal, the value will be 1770H. So now the next address will be after this value. So now the previous address is 4015, and now we have reserved this many bytes in the memory. So the next address will be 5785. And then again in this address also we have reserve word, but if you see it is only one word, so that means 3 bytes. So it is obviously 45788. And then we have 9AB, and then we have 57CDE. So now this is how we have to calculate the location counter. Now we will see how to write the object code. So while writing the object code, we have to check what is the opcode or the equivalent machine address given for each of the opcode. So for so let me write the location counters what we have done here. So this is what we have calculated now. Now we need to write down the object code for each of the instruction. So now this label, it represents the name of the program. Sum is the name of the program, and here we don't have any object code. So now because start, it just represents the starting address of the starting of the assembly language program. So now for a reference, I have just give the optab here, the machine equivalents of each of the opcode. So for the first one, the opcode is LDX. So the machine equivalent for LDX is 0, 4. So write 0, 4 and 0. So for 0, the label 0, we have calculated the addresses 5788. So write the addresses 5788. And then the machine equivalent for LDA is 0, 0. So write 0, 0. Then again the symbolic operand 0 has the address 5788. And then we have the address, the opcode is add. So for opcode add, the machine equivalent is 18. Now we have to carefully see this is a indexed addressing mode. So the label given here is the table. So for table, the address given here is 4015. But we cannot add this 4015 as it is, because since it is an indexed addressing mode, how we can do that is, so 4015, if we write in decimal, now the as we have seen the machine instruction format, the first 8 bits are opcode, and then we have 1 bit this X, and then we have 15 bits address. So this 15 bits, 4 8 12 plus 3 15. So this 15 bits is the address, and now this X bit, it is going to be 1. It's not going to be 0, it's going to be 1, because it is an indexed addressing mode. So when it is 1, so now again when you convert this value, you will be getting the hexadecimal value as C. So we cannot directly write 4015, but instead when we make this indexed addressing mode X bit as 1, it becomes C015. Then continuing with that, now TIX, the machine equivalent is 2C, and for count, the address is 5785. And then for JLT, the machine equivalent is 38, and for loop, the address is 4006. And then we have start. So sorry, total. So for for start we have, sorry, this is not start, it is STA. So for STA, the machine equivalent is 0C, and then we have total. So for total, the address is 578B. And then here we have seen that the operand, there is no operand given. So we can make the addresses 0. So before that R sub, we have the machine equivalent as 4C. And since there is no address, we can make it as 0. And then here we don't have any opcode, because these are all assembler directives. And for word, it is generating one word constant, so it is 0000, and reserve word assembler directive. Okay, so this is the object code that we need to generate based on the given machine equivalent and the addresses that we have generated. Now this has to be written in the object program format. So in the object program format, we have uh, three columns. The first one is header. Three records we have: the header record, the text record, and the end record. In the header record, the first column is represented using the symbol H to represent that it is header, and columns 2 to 7 it gives the program name. In our case the program name is sum, and columns 8 to 13 it gives the starting address of the object program in hexadecimal, and from 14 to 19 it gives the length of the object program in bytes. And text record, the first column represented by T, and column 2 to 7 it gives the starting address for object code in this record, and column 8 to 9 a length of the object code in this record. So for this particular record, what is the length of the object code? And from column 10 to 69, the object code to be represented in hexadecimal. So here we have to check that, see that for two columns is equivalent to 1 byte. And end record, the first column represents E, and then columns 2 to 7 it gives the address of the first executable instruction in the object program. So the object program, the code that we have found out, we are going to write it in the object program format. So the first column H, and this separator is just for our understanding, and in the original object code this will not be available. So just to separate to see to differentiate we are using that. So we have seen that the second uh, thing is 2 to 7 program name. So it means that 6 columns are available. So the program name, it is having only 3, it takes only 3 columns. So remaining 3 columns are free. And then the starting address of the object program. So the starting address of the object program, as we know, it is 4000. And then we have to find out the length of the object program. So how do we find the length of the object program is, we need to, the last address of this object program is 5780, and the starting address of the program is 4000. So that will give us 1780. So it means that, so since we are having 6 columns, 001780. And then text record. So in text record, we can see that the first we have to give the starting address for object code in that record, and then so for writing the object code we have totally 60 columns available. We have 60 columns from 10 to 69, so totally 60 columns are there. And if you see here, each of this is one column, it is taking one column. So now if you take now up to this point, we are having the addresses continuously, then we have reserved some few bytes, and then we are continuing. So if we take all these together, um, 1 2 3 4 5 6 7, so 7 object codes we have, and each object code is going to take 6 columns. So 7 into 6, 42 columns. So these 42 columns, it means that it is going to be 21 bytes. So this 42 columns can be easily accommodated in one text record. So starting from, we can see here 045788 is the first object code till 4C 0000. Till that all the object codes are included in this text record, and the length of the object code, length of this text record, we have to find it out. So how will we find out? We have seen that this 42 columns are there, so this is equal to 21 bytes. So this 21 bytes is nothing but, the in hexadecimal we have written it as 15. And then we have one more thing. So we have one more object code here. So we are writing it as a separate text record. and its starting address is this, and it takes only uh, the length of that object code is only 3 bytes, and the object code is given. Finally, the end record, it contains the first executable instruction, address of the first executable instruction, that is 4000. So this is the construction of object program. So based on this algorithm, we are going to simulate. We have to simulate the. We are going to simulate the assembler. So for any assembly language program taken, we need to have the input as the assembly language program, and we should have the optab, which involves the. We should have this optab, which contains the machine equivalents for all the opcodes present in the program. And we have to create a symbol table where we need to insert these symbols if it is not already available. And finally, we have to construct the assembly language. Thank you.